Our presenter today is Ron McLeod. In 2005, Ron was a founder of the ALS Burlington Life Sciences Laboratory and now serves as the technical director for Burlington. Ron has also served as a former general manager with Philip Analytical Services and former COO with Access Analytical. He received his Bachelor of Science and his PhD in organic chemistry from McMaster University. Ron is a specialist in air toxics, HRMS, and organic analytical chemistry. Today, Ron will be discussing organic flame retardants and environmental impact. Ron, thanks for taking the time to deliver this presentation. I'm about to turn it over to you.
Thank you. I hope you all can hear me and appreciate the attendance and the time that you're spending on this. Hopefully this will be a benefit. The intention here is to provide a general presentation, just an overview. It's not in great detail, it's just to introduce the subject, and we'll go over issues like defining the structures and target groups and what they are, what they look like, what their environmental concerns, and identify potential monitoring priorities if I can. So on the organic flame retardants, you can classify them in two broad categories. So on the organic side, from multi-component or polyconjugate as one grouping, and as also single component. And the multi-components include classes like diphenyl ethers, brominated diphenyl ethers, brominated biphenyls, chloroalkane, which are subcategorized into short, mid, and long chains. On the single component, there's melamine and its derivatives, phosphate flame retardants, and other halogenated targets. The melamine is not something I'll be covering today, and neither will I be covering anything on inorganic flame retardants. Fancy. Okay, and there's a bit of a moral conflict on the use of flame retardants. Of course, there's the benefit of prevention of fire, and however, there's the issues as far as environmental impact, and it's that conflict that sets partly the priorities of what's being used in the environment. Now, one of the problems in this field is, and it's not limited to this, but particularly once there's been a choice on flame retardants, they start being released to the environment. And unfortunately, environmental impacts generally assessments at that stage start rather than before they're released. So there's a phase delay once they become developed as to when we decide whether they're much of an environmental concern. But they always have the positive of being able to prevent people's deaths as far as flame protection and preventing flame and fires. And general properties of concern, of course, they're stable. These materials are added to all sorts of commercial products. They're pervasive in the environment because they're added to furniture foam, textiles, carpets, electronics. So the use is quite diverse, and they are used in percent levels in these commodity products. In order to be as flame retardants, they have to be at those sorts of levels in the products in order to do their job. And again, because they are being used in these commercial products, they have to be stable. Therefore, most of them are persistent in the environment. A lot of them are lipid soluble and bioaccumulative. And of course, because of their diverse use, there is a global distribution. So 8 out of 24 of the Stockholm Convention Annex A targets for eliminations are in the flame retardant class of compounds. I think that's a really important point because it identifies really how pervasive they are in the environment and how concerning they are. From that, of all the 24 types of targets that are chemicals that are in use, 8 of that are out of this class. So that is a serious environmental issue and concern. That statement right there identifies it. Now, although Certainly, most of them have relatively low mammalian toxicity, but many of them are toxic and the endocrine disruptors to other types of materials and species rather. Complications, of course, released levels in the environment, that's really high. There's perhaps inadequate knowledge on toxicity of all of these species. To all these species, but all of these targets, because as more come online, more needs to be done. And again, there's this phase delay to environmental release before we really understand the environmental impact. There are issues associated with analytical techniques to be able to see as low, so because despite the huge amounts that are being released in some matrices and in some of the target groups, there are significant analytical challenges to be able to see them at levels that are of value and interest to us as far as monitoring is concerned. And a lot of flame retardants are also used as plasticizers. That just enhances what they're used for. It doesn't really change the story here, but they are many of them are used for both purposes. Many of the products are used as mixtures in these commercial products, and so it's not usually just one thing, or not always just one thing being released from one product. Industry trends, there is a move away from the aromatic polyconjugate type materials because most of them have been identified as being problematic. So again, they're offering cocktails of single component products. And so there's now a different divergence of what materials need to be monitored. And the use of these single component products has a bit of a negative side in that clearly some of the manufacturers are, as soon as one is becoming notorious in the environment, they'll switch and go to another one of the customized targets, and we'll see some of those structures a little bit later on. So routes into the environment, how do they get into them? This is in rough order of importance. The municipal sewage is really where a large amount of it comes through, and laundry, and if you think of the things like textiles and carpets and furniture materials that get washed and so forth, or in contact with humans, because if they get in contact in your body system, they get cleared into the system. So all of that roots go into the municipal sewage. Other areas of product release, of course, would be landfill dumping of these materials and recycling and contact and aqueous leaching of the landfills and so forth. And of course, chemical manufacturing release would be a potential, but that's probably the lowest of the three possible entries. So now we get into the structures. I hope that this doesn't cause too much boring for some of you maybe chemists out there. So these are starting with the multi-component commercial types, and there are a variety of products. The first three groupings here, I have brominated diphenyl ethers, brominated biphenyls, and chlorinated alkanes. The latter two have mostly been stopped used for a while. The top one, the brominated diphenyl ethers, are being phased out, but are still in use as well. All of these targets are among the Stockholm Convention itemized, and the first one, in fact, represents three separate ones because depending on the level of bromination, there are multiple products that were released as far as commercial product groups. And all three of those groupings were identified in the Stockholm Convention. So the brominated diphenyl ethers have 209 possible congeners, but they're actually dominated when you brominate these structures as opposed to chlorination. Chlorination of biphenyl, you get mostly a large distribution of 209 congeners. When you go add bromine, it's a little bit more selective, or perhaps even a lot more selective. So you get certain isomers that dominate, and I've got those listed there. On the chlorinated naphthalenes, Again, this is chlorination, so when they chlorinate naphthalene, they again get a pretty wide distribution of a large number of congeners, although there are some that are at higher levels, just like PCBs, but still you get a very complex mixture of these things. And as far as the manufactured products is concerned, now another class, multi-component targets, is chloroparabens or chlorinated alkanes. They are generally sold and manufactured in three groupings of short chain, mid chain, and long chain. And these, what they do is they take alkanes or mixtures of alkanes, and they start just adding chlorine and chlorinating them. And when you look at, say, a C10 to a C13 range, which is the short chain chloroparabен range, you can get products which are 30% or 40% or 70% chlorination. Each one of those levels, when you imagine the carbon structure and the carbon length, whether it's an N-alkane or branch chain, when you look at the number of possible isomers of just chains, the number of possible levels of chlorination and the positions of chlorinations, you get into thousands of possible structures. And on the left side over here, what I have is an image of what you see by GCMS. If you're doing simple EI on these things, you just see a very broad band. And this is one of the analytical challenges. This grouping is of great concern environmentally, but it is almost being ignored because of the analytical challenges. So we're only now that we're coming up with methods that are effective at monitoring these things. And even at that, there's difficulty as far as how do you quantify them accurately in the environment. But still, the methods are now out there and are being used. But the analytical challenge on this is because you're looking at 1,000 possible or thousands of possible structures on any given product, and the response on chromatographically, because you're diluting this across 1,000 possible congeners, any individual congener has very little response, just because of the small concentration of an individual congener as opposed to the concentration of the grouping of them. So this has been a bit of an analytical challenge, and that's fortunately being resolved and more often being monitored. So these set of products have been manufactured in huge quantities and are still manufactured and added in huge quantities to a lot of products, although the short chain have mostly been eliminated from the immediate use. Of course, there's still legacy products out there that have lots of it, and there's lots of this stuff in the environment. On the phosphates, we have a general structure over here of a phosphate with triesters, so 3 alkyl groups. Those alkyl groups, of course, can be the same or different ones. More often, they're the same in the products that are being supplied. And these represent the general structures. There's both aryl and alkyl. The aryl ones are the ones that are better as far as flame retardants as well as plasticizers. These ones also have some flame retardant properties, but are more commonly used as plasticizers. Same issue. They're released they're in enormous levels. And when you look at certainly municipal waste waters, then you'll see very high levels of all of these guys, or most all of them. So this represents another problem, and a lot of them have been identified as being endocrine disruptors and problematic as far as aquatic areas is concerned. So other halogenated flame retardants, and now we get into a potpourri and a wide distribution of different individual compounds that have been used and are in use. One here, which is the hexabromocyclododecane, is again one of the items that has been identified in the Stockholm Convention for elimination. But most of these things are, just generated fairly new products that come along. And this is just one page. There's another page that I've shown of other examples of structures. So another 6 possible structures, and what you're looking at is ways in which they've come up with organic molecules in which they've been able to add bromines and or chlorines onto them in order to make them have flame retardant properties as well as organic, since they would have an affinity for the products, commercial products that are being sold. So again, a plethora of different targets. Now, as far as levels, expected levels and environmental methods is concerned, this is a table providing you with a distribution of what you normally see. The first two I've put at the top because they're the ones that are being released at the highest levels, and really at almost alarming levels that they are being put out into the environment. Analytical techniques I have on the right-hand side, although that's not complete. Chlorophenols are done by generally a special ionization technique. One of the problems with the chlorophenols is that from a mass spec standpoint, if you do a normal ionization technique, which is EI, electron impact, these things fragment so that you can't actually see any structural information on them. So, and it also makes it very difficult to identify them and not very responsive. So there's special techniques. One of the ones is electron capture, negative ionization. This can be done by low res and high res. There's also what's called Orbitraps to be able to obtain information. We're doing this by GC low res, MS, ECNI. That's our technique. It's others are using that as well. But other than that, if you're going to a more esoteric approach, it's mostly done by researchers. Phosphates, some of them are GCable, some of them can only be done by LC, so there's various techniques on those ones and target lists. They're not particularly difficult to analyze for because of the levels. There are pretty high levels, especially on the effluent and emissions and so forth. The other ones, brominated diphenyl ethers, brominated biphenyls, PCNs, hexabromocyclododecane, dechlorine plus. These are ones that have been around actually for a while. We have some pretty routine techniques on the diphenyl ethers and the brominated biphenyls. We also have an internal method for doing PCNs. All of these we're doing here by high-res MS. And the brominated diphenyl ether, the EPA reference method is 1614, which is what we do and is offered by high-res. That's a high-res MS method. Some of these things what I've missed on the dechlorine plus and the other flame retardants, they can actually be done also by low-res ECNI. So as they say, the table's not complete. But again, the general gist is the top of the table are the ones where there are much higher levels being released. It doesn't necessarily mean that they're being higher level released, that the lower level ones aren't of concern too. They all are, but then there's a relative risk associated. So certainly concern of the higher ones generally have higher concern. So what are your challenges? What ones do you need to be monitoring for, and what ones do you choose in your programs to be looking for as far as consultants? And that I don't have great answers for, in that these things many of them have difficulties as far as detectabilities. The methods most of them are not necessarily routine or specialty, so the costs generally are high. But they are important targets to be monitoring. If you're trying to design a program, which ones should be on your target lists? What ones ensure that what your program is relevant, and what labs are offering? We're offering all or most of these things, but they're not actually that easily found. They're not that many labs that are doing some of these, and a lot of the work that we get on this sort of thing is publicly funded research programs and RFPs, where they're trying to identify the levels. The sorts of things that are much more routine, brominated diphenyl ethers is a pretty common one. but the other ones are not any less of environmental concern necessarily, but the analytical techniques have not been out there that long. And so I think what you will see is more emphasis on some of these things, and these targets will come up more and more on your radar scope. Now this slide here, I'm going to apologize a bit for the slide in that it's a bit of a work in progress. I was trying to present something about levels and risks and factors associated with risks. The items of the table where I've got yellow are indicating risk, higher risk and higher concern. So in the general columns here, the first column here is it Stockholm Convention target, and a lot of them are yes. So obviously that represents an independent agency identifying there's concern. Current production level, ones that are in huge production are the ones that I have listed in yellow here. Legacy products, major or minor, and so forth is in this column. The next column on environmental toxic concerns. In general, the answer to that is yes. If I go across this page, for example, on short chain chlorparaffins, there's a difference here between mid chains and long chain. The short chains have been identified as certainly environmental concern. There's controversy on these ones. I think you'll find in the very near future the mid chain chlorparaffins will also be on this sort of target list. Expected levels are in this column, so the ones with the higher levels I've given a higher number, and the ones in larger production numbers, which of course correlates well with the expected levels, are also in yellow. So this is maybe a bad table, but trying to represent the factors associated with risk assessments, the crude risk assessments that may be of concern as far as what products to be monitoring, what ones to be looking at. And in summary, and I hope this has been a fairly short presentation providing an overview of what is out there, what you should be concerned about, what are emerging concerns. All these target groups of environmental concern, chlorparaffins and phosphates, are identified specifically here because of the levels, extremely high levels that they're being released at. Individual halogenated flame retardants, I think, need more attention because of the issue as their environmental impact is less known, and so there needs to be some level of attention on that one. So that's the basis of my presentation, and so the next mode would be to answer questions, if there are some.
Thanks, Ron. We will open it up for questions. You can either write out your question in the chat section at the bottom right, or update your status to raise your hand to verbally ask Ron your question. We'll give everybody a few minutes. We have a question. Target 2 compounds and phosphates are originating from which types of products?
I'm not sure. I'm assuming that you can hear my verbal responses here. I'm not sure all of the different products the phosphates are being used in. They're certainly heavily used in textiles. That much I know. They're used in some of the electronics as well. I don't have a great answer for the broad scope. Now, target 2 compounds, I'm not sure which compounds they're asking about on that. Go back on slides. Are we talking about? I'm not sure what the single component, is that what they're meaning by target 2? Chlorinated.
Yes, Pam says.
Oh, Pam, chlorinated paraffins. Yeah, chlorinated paraffins are again used in a wide variety of products, a lot of electronics, certainly in textiles as well. They're also used in other purposes. Actually, they're used as far as we call them. They're oils used for cutting oils. That's another application which is also related to flame retarding in that it's preventing the cutting oil from flaming while you're cutting metals. So when you're drilling metals and so forth, the cutting oils that are used have the chloroparafins in them.
If we don't have any other questions, I will wrap this up. Thank you again, Ron.
No problem.
Remember, we will be posting this and notifying you by email. Thanks for attending and enjoy the rest of your week.